Good afternoon. My name is Samir Kumar Chauhan. I am a final year student of Information Technology and Computer Application from Madan Mohan Malviya University of Technology. I am here to present a presentation on IoT-based home automation solution under the guidance of Ma'am Jayalakshmi N. Dhanyal. Before moving in detail, let's talk about the internship. So this internship is based on IoT home automation using Blynk IoT Cloud. The main aim of this project is to make students to expose to what IoT is and various applications of IoT. Initially, the internship start introduction to C and C++ programming, and then we learn a briefing about IoT embedded system and then implemented small basic project. The final project in this internship is implemented using Arduino IDE and PicSimLab simulator and Blynk IoT mobile application. Here what we have learned during this internship. So we first learn a C programming which include various things which will be discovered later. After that, a brief introduction to OOPS in C++, IoT, embedded system, Arduino IDE and PicSimLab simulator. Blynk IoT integration in which we focuses on how to integrate the code with the Blynk IoT application and interfacing the serial time. The topics we covered in C programming are number system. Number system are the method used to represent numbers in different ways. Common number system include the binary decimal which has base 10, octal with base 8, hexadecimal with base 16 and binary with base 2. After that, data types. Data types define the type of data a variable can hold, such as integer, floating point, number, characters and more. Conditional statements. A conditional statement allows the execution of certain code block based on specific conditions. The most common conditional statements are if, else if, and else. Operators. Operators are symbols that perform operation on variables and values. Examples include arithmetic operators, comparison operators, and logical operator, etc. Arrays. An array is a collection of elements of the same data type stored in contiguous memory location. Array allow you to store and access multiple values using a single variable name. They are useful for managing large amount of data efficiently. Pointers. Pointers are variables that store the memory address of another variable. They are powerful tool in C++ programming, allowing for dynamic memory allocation, efficient array management, and creation of complex data structure like linked list. Functions. Functions are blocks of code that perform specific tasks and can be reused throughout the program. Functions help to organize code, reduce redundancy, and improve maintainability. They can take inputs and return output. Storage classes. Storage classes define the scope, visibility, and lifetime of variables within a program. Common storage classes include auto registers, static, and extern. And the last is macros, header files, and preprocessors, where macros are preprocessors directives that define constants or expressions. Header files contain declaration of function and macros that can be included in multiple source files. The preprocessor processes directives before the actual compilation, allowing for code modularity, and reusability. These tools are key to writing efficient and organized C or C++ program. Internet of Things. The Internet of Things or IoT refer to the network of physical objects connected to the Internet, enabling them to collect and exchange data. In our project, we simulated an IoT-based home automation system using PicSimLab, focusing on how IoT can remotely control and monitor devices like lights, temperature, and water level. Through the Blynk IoT app, we simulated real-time control and monitoring these devices, mimicking how IoT work in actual smart home systems. This simulation allowed us to explore practical application of IoT in automating everyday tasks, providing a deeper understanding of how smart technologies can be implemented even in a virtual environment. Some of its key components of IoT are sensor or devices, which is used to collect data from environment, connectivity to transmit the data to the cloud or other devices, data processing, data processing to analyze the data for meaningful insight, and the user interface to provide user with actionable information. Some of the application of IoT are in smart homes, example, smart thermostats, security system; in healthcare, wearable health monitors; industrial in industrial automation, example, predictive maintenance; and in agriculture, we can use them as in precision farming. Embedded system. Embedded systems are specialized computing systems designed to perform specific tasks within a large system, often with real-time constraints. In our project, we simulated embedded systems using PicSimLab, focusing on how these systems manage tasks like reading sensor data and controlling devices in a home automation setup. We worked with Atmega 328P microcontroller within the simulator to emulate the behavior of real embedded system, handling tasks such as monitoring temperature, controlling lights, and managing water level. This simulation-based approach allowed us to gain a deeper understanding of embedded systems and their application in automating smart home devices. Some of the characteristics of embedded systems are: they are tailored for specific tasks. These are often required to perform tasks within a strict timing constraint. They require limited memory, processing power, and energy consumption, and they are high dependability, especially in critical applications. Its example contain in consumer electronics, example, smartphones, smartwatches; in automotive system, example, engine control unit, airbags; medical devices, example, pacemakers, insulin pump, etc. And in industrial machine, embedded system can be used in CNC controller or robotic arms. Arduino IDE. The Arduino IDE is an open source integrated development environment platform which is used for writing and uploading code to microcontroller board, including those simulated in environment like PicSimLab. In our project, we used Arduino IDE to develop and test code for the Atmega 328P microcontroller, simulating its operation in a home automation system within the PicSimLab simulator. This IDE provides us with user-friendly environment to write, compile, and debug our code, ensuring that our simulated embedded system functioned as expected. Using the Arduino IDE in a simulated environment, gave us valuable experience in embedded system programming. Its key features are it has easy to use text editor and toolbar, contain extensive collection of libraries for various sensors, modules and functions. It has tool for real-time debugging and communication with Arduino board, and it is available for Windows, Mac OS and Linux. Its common uses are for developing and testing code for embedded projects, prototyping IoT application, and learning and teaching electronics and programming. Now PicSimLab. PicSimLab is a powerful simulation tool designed for developing and testing embedded systems. Using PIC microcontroller, it provides a virtual environment where we can simulate various aspects of our hardware project. For our project, we use PicSimLab to simulate a home automation system. This allowed us to develop and test our embedded system without needing physical hardware, which is particularly useful for prototyping and validation. With PicSimLab, we could emulate the behavior of the Atmega 328P microcontroller and its peripherals, such as sensors and actuators, to ensure that our system responds correctly to different conditions and outputs. The simulation environment offered features like real-time debugging, variable monitoring, and step-by-step execution, which were crucial for troubleshooting and refining our code. This virtual setup mirrored the real-world interaction we would expect in a physical implementation. Overall, PicSimLab provides us with cost-effective and efficient way to design, test, and optimize our home automation system, demonstrating the value of simulation tool in embedded system development. Its working is, first of all, we will upload our program in the format of .hex file in the PicSimLab simulator, and then the output will be observed on according to the parts we used. Now what we have done in the internship. So during my internship, I worked on implementing a home automation system which was simulated using PicSimLab. This project focused on automating household devices such as light, temperatures control, and water level sensor. We begin by designing the system architecture and selecting appropriate PIC microcontroller for simulation. PicSimLab allowed us to create a virtual environment to develop and test our embedded system without physical hardware. I wrote and tested the control code using the Arduino IDE, which was compatible with simulated Atmega 328P microcontroller. This approach enables us to validate our system's functionality and performance in a simulated setting. Throughout the project, we utilize PicSimLab debugging features to troubleshoot and optimize our code. This included real-time monitoring of variables, setting breakpoints, and stepping through the code to ensure accurate operation. The project also involved integrating the Blynk IoT app to simulate real-time control and monitoring of the home automation system. This demonstrated how IoT technologies can be applied in a virtual environment to manage and automate household devices. By the end of the internship, we successfully simulated a functional home automation system, which provided valuable insight into embedded system and IoT application. This experience enhanced my skill in simulation, coding, and system design. Our home automation project was divided into four key components, each addressing a specific aspect of our home management. These components are garden lights control, temperature control system, water tank, inlet and outlet valve control, and integration with Blynk application. In garden light control, system aims to automate garden lighting based on the sunlight availability. Using an LDR sensor, the system continuously measures ambient light level when the sunlight is low. The system reads a lower value from the LDR sensor, which triggers an increase in LED's brightness to simulate the garden light turning on. Conversely, when the sunlight levels are high, indicating daylight, the system reduces the LED's brightness or turn it off, reflecting a decrease in garden light activity. This approach ensures that the garden lights are efficiently managed based on real-time light conditions, enhancing both convenience and energy efficiency. Temperature control system. The temperature control system consists of several components which include a heating resistor, an LM35 temperature sensor, a cooler, a CLCD, and a Blynk IoT app. The system uses the LM35 temperature sensor to measure the current temperature. This temperature data is displayed on the CLCD and gauge widget within the Blynk app. User can control the cooler and heater through the button widget on the Blynk app, which allow for remote management of these devices. The process includes reading the temperature and allowing it on the CLCD and gauge widget. The system toggles the cooler and heater on or off based on the state of the button widget in the Blynk app. If the temperature exceeds 35 degrees Celsius, the system will turn off the heater, send a notification via the Blynk app, and display an alert on the CLCD to inform user of the high temperature. The output of the system includes displaying the current temperature on both the CLCD and gauge widget and controlling the status of the cooler and heater through the Blynk IoT app, with feedback provided to the user on the system's status. Water tank inlet and outlet valve control. Water tank control system integrates several components: a water tank, a CLCD, serial communication, and Blynk IoT app. The system uses serial communication to read the water volume from the tank. This volume is displayed on the CLCD. Users control the inlet and outlet valve via button widget in the Blynk app. The process includes reading the water volume and displaying it on the CLCD. The system toggles the inlet and outlet valve on or off based on the state of the button widget via serial communication. If the water volume drops below 2000 liters, the system activates inlet valve, send a notification to the Blynk app, and display an alert on the CLCD. Blynk application. The Blynk application enables remote control, monitoring, and visualizing of IoT devices in our home automation system. It provides a user-friendly interface to manage and oversee various components from a smartphone. It contains widgets, which include button widgets. The app includes button widgets that allow users to control the heater, cooler, inlet valve, and outlet valve. These widgets facilitate remote operation on these devices, making it easy to manage the system from anywhere. Threshold control. In heater, the app is configured to automatically turn off the heater if the temperature exceeds 35 degrees Celsius. This action is accompanied by notification displayed on CLCD with the message HTR off, ensuring users are informed of the heater's status. Water tank. The app monitors the water tank status and will automatically turn off the inlet valve if the tank is full. Notification is also shown on CLCD to alert user of the valve status. Now let's move to the code. So this is the code of our home automation system. Here we have defined the Blynk template ID, Blynk template name and Blynk authentication token, which is necessary to create a connection between this code and the Blynk IoT application. And then here we included some header files which contain some values and functions name. These are all header files and the liquid crystal I2C and the Blynk timer. Here the Blynk write function is created for cooler VPN, which is used to control the cooler with the Blynk IoT application. And this Blynk write is used to control the heater VPN, and then Blynk write is used to control the inlet of the water tank, and this is used to control the outlet of the water tank, and this update the temperature reading, handle temperature, handle tank, and this is a setup which will be declared in this, which require only one times, and the function which needs to be repeated on a regular interval will be defined in this loop section. And here are the various files that can be imported in this main file. Now moving to the simulator. So here is the simulator. On decreasing the LDR sensor, the light is dimming, and on increasing, the light increases. So here is a garden light sensor. On toggling of the cooler switch, the fan started moving, and here is cooler on and the temperature rising, as it also always below the. On increasing the heater switch here is indicating that the heater is on and the temperature start rising. And when the temperature reaches 35 degrees Celsius, it should be turned off. Let's see. Here the heater is automatically turned off as it reaches above 35 degrees Celsius. And when we turn off the cooler switch, turn on the cooler switch, it's indicating that the cooler on and the temperature will rise with speed. Let's just turn off this. Now moving to the water tank. Uh, Here is the water tank. When we turn on the inlet valve, here it's indicating that the inlet flow is on and the water start filling. And when the tank is full, which is 3000, the inlet flow is already off, automatically off. And when we outlet turn on the outlet valve, it's indicating that the outlet flow is on. And when the water level is below 2000, the inlet valve should automatically open, which is happened. Here inlet flow is on and the outlet flow is off. So this is basically our project which we have implemented. Thank you.